Hello everyone, my name is Yunseon Shin from the Parallel System Architecture Lab at PostTech. In this session, we will walk through the basic uses of PyTorchSim. Let's get started. Let me first walk you through what we will be covering in this session. In part 2, we will go through the basic uses of PyTorchSim. Before we dive in, let's set up the environment. Please open a browser and navigate to the link. Once you land on the login page, click the sign up. Enter your desired username and password, then click Create Users. After that, log in using the account you just created. If you run into any trouble connecting, please don't hesitate to ask for assistance, and we will help you right away.
If you have any problem, just raise your hand and our organizer will be able to help you.
So, sign up and username. Click Create Users, and you can click the login. You can connect your account. Okay, all right. Is everyone all set? Please raise your hand if you are still having trouble logging in. Once you successfully logged in, you should see a screen that looks like this, the Jupyter Lab interface. Now, let's get into the actual content. The first topic is running PyTorchSim. The key message here is simple. You only need to change the device setting in your existing PyTorch code. Here we have a simple member example. As you can see, the device is set to either CUDA or CPU, and it performs a matrix multiplication. To run this with PyTorchSim, all you need to do is change the device to MPU. Everything else remains exactly the same. Now let's look at what actually happens. Calling the compile function runs the MPU simulation and returns the result value. So now it's your turn. Let's run your first MPU simulation with PyTorchSim. Open Inference Notebook, and you can run cells one by one or to execute all cells at once. After running, check if the CPU and MPU simulation outputs match. You can open the notebook with this link. And execute all cells. Okay. After running both OR cells, you can see the simulators running in the low. Then we call test result function to compare the NPU and CPU outputs. As you can see, the output values match. If you have any issues, please raise your hand. Okay, let's move on. The same principle applies to training as well. Here we have a simple backward pass example. The device is set to CUDA or CPU, and it performs matrix multiplication followed by a backward pass. To run this with PyTorchSim, all you need to do is also change the device to NPU. Everything else remains exactly the same. Let's look at what actually happens. First, optimize function runs the forward simulation on NPU. Then, backward function runs the backward simulation on NPU via PyTorch AutoGrad. Okay, now it's your turn. Open training notebook and click the Run All Cells button here or run cells one by one. After running, check if the CPU and NPU simulation gradients output match. So click the link. Run all cells.
Question, so can you explain the output? Why is not the why is the CPU and the numbers matching? It's supposed to be the same.
We should validate the generated RISC-V NPU binary. So we compare the CPU output and NPU output. Yeah.
So the intention here is that we are trying to validate the output from the NPU simulator with the golden output. The golden output in this case is from CPU. You can obtain from other devices, but we are comparing them to demonstrate that the simulator produced the correct output.
So I don't understand why would the NPU and the CPU have exactly the same runtime?
Oh, does it have this runtime? So runtime, why is
runtime 다르다.
is the runtime same?
I mean, not the number and the output.
Number.
No, this is that's the output. Oh, that's the output. That is not the time. Oh, I see. This is the functional. Yeah, functional.
Yeah, functionality, yes.
Yeah.
헷갈리신 거. functional test인지 모르셨다.
아니 몇 시간이 갔냐고 펑션 테스팅을 하려는데 몇 시간이 갔냐고
시간이 어디가?
Where is the time you're referring to?
No.
헷갈리시네.
I thought it's the runtime, but it's actually just a functional test.
Right? It's functional test. Yeah. We're not modeling the timing this time.
Yeah.
Okay, thank you for the question. So after running you can see the simulators running in the low. Then we compare the NPU and CPU gradients output. As you can see, both the input and weight gradient values match. Now, let's talk about mapping. When running computation on hardware with limited on-chip memory, we can load entire matrix at once. Instead, we use a technique called tiling, breaking large matrices into smaller tiles that fit in the scratchpad memory. The choice of tile size can have a significant impact on performance, which is why PyTorchSim offers multiple mapping strategies. PyTorchSim provides 3 mapping strategies. First is heuristic, which is the default. It maximizes scratchpad memory uses under a double buffering scheme. The second is external, which reads tile size for each gem shape from an external configuration file. If a shape is not found in the file, it falls back to either heuristic or autotune. The third is autotune, which automatically searches for the optimal mapping by trying different configuration and selecting the fastest one for the given hardware and workload. Its search space includes heuristic-based candidates as well as various vector length strides. So mapping strategies are configured through the PyTorch config. The relevant parameters are cogent mapping strategy, and for external mapping, cogent external mapping file. The 4 valid string values for the strategies are heuristic, autotune, external then heuristic, and external then autotune. The last 2 will try the external file first and fall back to the specified method if no entry is found. Alright, now it's your turn. Let's compare all 3 strategies on the same matrix multiplication. Open mapping notebook and run all cells. You can see the very long logs, and scroll down your log, you can find the total execution cycle. With heuristic mapping, PyTorchSim select tile M is 1024, tile N is 1024, and tile K is 256. The total execution cycle count for this configuration is about 50K cycles. For external mapping, you provide a JSON file like this. The key is string of the format M and K, representing the gem shape, and the values specified tile M, tile N, and tile K, which is user-defined tile size. So with this smaller tile configuration, the total cycles increased to about 57,000 cycles. And then autotune select tile M is 1024, tile N is 1024, tile K is 256, the same as heuristic in this case. It shows that heuristic finds the optimal mapping well for this shape. let's move on. Now I will talk about execution mode. PyTorchSim supports 3 execution modes. The first is functional only mode, which uses only the spike simulator. This is used for DNN accuracy validation. It checks that the numerical results are correct without simulating timing. The second is timing only mode, which uses Gen 5 and TorchSim, but skips functional simulation. This is ideal for inference performance evaluation or single iteration training evaluation, where you only care about cycle counts and don't need to track data values. The third is functional and timing mode, which is the default. It uses all components, Spike, Gen 5, and TorchSim together. This is used for full training performance evaluation and data-dependent torque evaluation, where both correctness and timing matter. You can enable or disable functional and timing mode via PyTorchSim configuration. So let's compare the 3 modes: Open Execution Mode, Notebook, and Run or Cells. Okay. After running all cells, in the default functional and timing mode, you can see all 3 simulators being invoked: Gen 5, Spike, and TorchSim. The total work clock time is about 8 seconds. In functional only mode, only Spike runs. The work clock time drops to about 1.3 seconds. In timing only mode, only TorchSim runs. Work clock time is now about 500 milliseconds. You can select a mode depending on your needs. Okay, now let's go deeper into TorchSim itself. We'll cover 2 aspects: how to configure it and how to analyze its output logs. TorchSim integrates 2 cycle accuracy simulators for memory and interconnection modeling. The first is Remulator, which is a cycle accuracy DRAM simulator. In the configuration, you specify parameters like DRAM type, frequency, and number of channels. And the second is a BookSim, a cycle accuracy interconnection network simulator configured with parameters like interconnect type, frequency, and number of ports. Here is an overview of the full TorchSim configuration file. It's organized into several sections. The core configuration specifies the number of cores, clock frequency, and systolic array parameters. The DRAM configuration specifies the memory type, frequency, number of channels, and emulator config. The simple NOC configuration sets the interconnection type and latency. The PyTorchSim functional mode and PyTorchSim timing mode flags control the execution mode as we discussed. The codes and configuration controls mapping strategies and compiler optimizations. And if you want to use booksim instead of the simple NOC model, you can specify a booksim configuration file. Okay, it's your turn. Let's see how the number of cores affects simulation. Open TorchSim config notebook and run all cells. The notebook runs a 2048 by 2048 matrix multiplication. Okay, open your notebook and run all cells. Okay. After running all cells with a single core configuration, the memory takes about 300,000 total execution cycles. With 2 cores, total execution cycles drop to 160,000 roughly, which is close to ideal linear scaling. Okay, let's move on. PyTorchSim produces 2 categories of output files. Dump files stored in TorchSim dump contains all the intermediate files like TOG, MPU binary, and so on. The log file stored in TorchSim log path contains simulation result. There are 2 verbosity levels, info level, which gives you high-level statistics, and trace level, which records cycle-by-cycle execution events for detailed debugging. Each compiled kernel gets its own subdirectory under the dump path named by a hash of the kernel. Inside, you will find the cycle bin, the binary for Gen5, and the validation binary for Spike, the tile graph Onyx, which is the TOG, and several runtime attribute files. You can inspect the MLIR and LLVMIR files to understand what code was generated for your workload. When TorchSim log path is set, the simulation logs are saved to the TorchSim result directory with file names in the format datetime hash.log. You can see in the file explorer that both log and trace files are generated for each simulation run. The log file contains info level output, while the trace file contains the list of executed kernels. Okay? The notebook sets the TorchSim log path environment variable to a further called info result. Now it's your turn. Open info log analysis notebook and run all cells. After running this cell, you can find the info result directory. After running the notebook, navigate to the info result folder. You will see a .log file and a .trace file, both named with the timestamp and kernel hash. So open the generated log file in info result. And open the .log file. When you're opening the .log file, the first section prints the full TorchSim configuration that was used for this simulation. All the hardware parameters we discussed earlier. Below that, you can see the Remulator 2 configuration. Further down in the log file, you can find several important statistics, DRAM stats, instruction stats, and core stats. Finally, at the very bottom, you can see the total execution cycle and the word clock time for simulation. So now, to enable trace level logging, simply set the environment variable TorchSim debug level to trace. This notebook set the log path to trace result. So now we open the notebook and let's run these all cells. Okay. After running the cells, you can find the trace results directory. Then navigate to the trace result folder and open the .log file. Not the .trace file, but the .log file, which now contains both configuration info and cycle level trace data. At trace level, you can find the tog node information. And later in the file, you get the cycle level simulation events. Each line records a single event with a timestamp. You can see when the tile is scheduled and instructions are issued and finished. Okay, let's move on. Now, let's talk about compiler optimization. PyTorchSim's compiler supports three main categories of optimization. The first is fusion, which reduces off-chip memory traffic by merging dependent kernels into a single kernel. As shown in the diagram, instead of having two separate load compute store sequences for operation F and G, Fusion combines them into a single load compute store sequence, eliminating the intermediate store and loads between the two operations. The second category is convolution optimizations, specifically single batch and multi-tile convolution. The third is fine-grained DMA, which improves overlap between computation and memory transfers. Let me explain fine-grained DMA in more detail. As I mentioned before, the tile size can significantly impact performance on NPU. However, in a standard tiled gem, computation on first tile has to wait for the entire tile DMA to finish. This is what we call coarse-grained DMA. You can see there are some bubbles, but in fine-grained DMA, each tile is further subdivided into subtiles, which allows more overlap between DMA and computation. Compiler optimizations are controlled via the CodeGen compiler optimization field in the configuration file. The default is all, which enables all optimizations. You can disable everything with none. Or alternatively, you can specify individual optimization such as fusion, convolution, and fine-grained DMA. You can also selectively enable specific optimizations by listing them as a comma-separated string like this example. Alright, let's compare the impact of fusion on a gem followed by the value. Open compiler optimization notebook and run all cells. Open notebook. And run all cells. Okay. With fusion enabled, the gem and value are merged into a single kernel. The total execution cycles are about 53K. And with fusion disabled, the total execution cycles are 133,000, roughly 2.5 times more than the fused version. Next, you can also visually inspect tile operation graph using Netron, a popular neural network model viewer that supports Onyx format. From your browser, navigate into a fused or non-fused directories under your dump path. You can open non-fused directory with this link. And enter into the hash directory. Download the tile graph Onyx file. You can download all those GeoGIS, but I just download only one, this ReLU talk. So you can download the talks, and we will have 2 non-fused talks and 1 fused talks that combines them. Go to Netron in your browser and click Open Model. Select the Onyx file you downloaded. Click the Open Model. Open your Onyx file. And you can see the TOG in this browser, and you can select the node, and there's some details about the node. Oh, if you select the compute node, you can see the attribute of the compute node. There's some TorchSim cycles. This is computed in the Gen 5 simulators in offline. Okay, let's move on. So here are the 2 separate TOGs built in Netron before fusion. On the left is the ReLU talk, which is relatively simple. It consists of loop start, load, compute, store, and loop and nodes. On the right is the gem talk, which is much more complex with multiple nested loops. And here is the fused talk. Comparing it to the separate gem talk, the structure is similar, but at the bottom, you can now see a ReLU compute node inserted directly after the gem compute section before the final store. Okay, it's the last session. Finally, let's look at the DNN serving simulation feature. PyTorchSim supports us simulating not just a single model execution, but a realistic serving scenario where multiple inference requests arrives over time. The Poisson request generator function generates arrival timestamp following a Poisson process. And the key API for this is TorchMPU launch model. You pass in the compiled model its input arguments, a stream index that maps to a hardware partition, and the arrival timestamp. The stream index corresponds to a hardware partition defined in the config. The timestamp parameter tells the simulator when each request arrived, so it can compute end-to-end latency, including any queuing time. All right, let's run the full serving simulation. Open load generator notebook and run all cells. I think it will take about 5 minutes. Yeah. Okay. I think we don't need to wait. And next slide, there's some result. The simulation result shows about 6 million total execution cycle for the ResNet 18 workloads. So, okay, I will leave up here, and if you have any questions, please feel free to ask. Thank you.